Well, let's see if that starts showing up eventually. Let's see if that shows up. There we go. Cool. Let's see. All right. Should I share my screen in Discord too or no? All right, then. Let's see. On Discord? Let's see. There we go. All right. And then you can see it without the 15 seconds of delay. All right, so I guess we can get started then. Well, this is the first workshop, I guess, that we're having as part of the CTF workshop, and it's on like crypto basics. But first, there's just a few announcements. The mentor-mentee assignments, they've been made, and the mentors should be getting with their mentees in the next few days. And not everyone who signed up was able to make it because there were lots of sign-ups, and we only have limited resources, specifically limited number of mentors. Maybe next semester, if we do this, we'll be able to have more people on both ends. All right, so the first thing to cover with regards to crypto is just basic encoding schemes. And the most basic of that is just numerical bases. So a numerical basis is just a way to represent the concept of a number, and it's a sum of multiples of the powers of a base. So it's normally from right to left is some digit times base to the 0th power, some digit times base to the 1st, plus some digit times base to the 2nd, and so on. And each digit can have the value from 0 to base minus 1, because if you have more than that, then it could become base times base to some power, which is just base to the next power. And the most common base, one that most people are probably familiar with, is base 10 or decimal, which your standard 0 through 9, and 123 is 1 times 10 to the 2nd plus 2 times 10 to the 1st plus 3 times 10 to the 0, or just 1 times 100 plus 2 times 10 plus 3 times 1. And you're probably taught that in elementary school, like 1st grade or something, how numbers work. But most people don't remember that, especially if we go into stuff like binary. Binary is often denoted in groups of 4 or 8 bits, but here sometimes in these slides I'll use a 0B prefix just for clarity. And obviously it's base 2, and that means the digits can be 0 or 1. So 1110 is 1 times 2 to the 3 plus 1 times 2 to the 4 plus 1 times 2 to the 1st. Did I say 2 to the 4? 2 to the 2nd plus 1 times 2 to the first plus 0 times 2 to the 0, which is just 1 times 8 plus 1 times 4 plus 1 times 2 plus 0 times 1. And that's 14 in decimal. And computers especially love binary because the digits can all be represented as high and low voltages. And another common base is hexadecimal or base 16. The digits used are 0 to 9 and A to F. It can be either lowercase or uppercase. It generally doesn't matter. And you'll see a 0x prefix, and sometimes it'll just be in groups of a power of 2. So you'll see groups of 2 digits or 4 digits or 8 digits, generally not more in normal applications. And each digit has a value 0 to 15. So we needed some other digits for values 10, 11, 12, 13, 14, and 15, because we can't just write 10, 11, whatever. So the easiest option was A through F, because they're the first letters. And 0x 1, 2, 3 is 1 times 16 to the second plus 2 times 16 to the first plus 3 times 16, which then becomes 1 times 256 plus 2 times 16 plus 3 times 1, which is 291 in base 10. And base 10 or base 16 is the same as base 2 to the 4, which makes converting between binary and hexadecimal pretty easy, because each digit 0 to 15 is just binary digits 0000 to 1111. So each group of 4 bits becomes 1 hex digit, and vice versa. Each hex digit represents a group of 4 bits. And 0x42 becomes 01000010, which you can look at each group of 4, and it represents 4 and 2, and that's 66 in decimal. Because of that, hex is a common way to represent binary in a more compact form, which is nicer for humans to read. Base 8 or octal is another fairly common numerical base, and it has a 0 prefix, or sometimes it's just groups of 3. And the digits are 0 to 7. So 0, 1, 2, 3 would be 1 times 8 to the second plus 2 times 8 to the first plus 3 times 8 to the 0, or 1 times 64 plus 2 times 8 plus 3 times 1, which is 83 in decimal. Similarly to hex, you can convert between binary and octal in a pretty nice way, because base 8 is just base 2 to the 3. So each digit 0 to 7 becomes binary digits 000 to 111, where each group of 3 bits in this case represents 1 octal digit. And any power of 2 base works in a similar way. You could have 32 or you could have 4. They would have a nice little grouping of bits for each digit. Now, 042 becomes 100010 from octal to binary, which is 34 in decimal. Now, octal used to be a lot more common when computers used memory that were multiples of 6 instead of multiples of 8 bits, like they are today. And it's not super common anymore, but you still see it in stuff like Unix file permissions, because there's 3 special permissions, which is the set UID, set GID, and sticky bits. And then there's read, write, execute permissions for user, read, write, execute for group, and read, write, execute for other. Those are all groups of 3, so using octal makes sense for representing them. So you'll see the the numerical representation of Unix permissions are octal digits. Now, we also need a way to represent text as numbers so that computers can understand them. And just like regular text, each character needs to have a unique code. So ASCII was created because there were competing standards used by different companies or different machines, but ASCII is the most common today. It defines a value for each letter, number, and your symbols that you see on your keyboard, but there's also non-printable control characters such as line feed or new line, as it's also known. And there's also a delete character, which is at the very end, but between there are all your printable characters. And you can see a pretty nice website just to look at the ASCII table is ASCIItable.com. And if you're on a Unix or Linux machine, man5 ASCII will give you a man page that just has an ASCII table. So then here's just the ASCII table in decimal, and 32 is space, and that's the first printable. And then the same thing in hex as well. Then it's also useful to go in the opposite direction and encode binary data as text. And this is useful for stuff like email or some other thing where you want the data to remain intact after processing. So you don't want any data to be lost. For example, if you're printing off a program for some reason, there's going to be a lot of data that's lost. But if you encode it as text and print it, then I suppose in theory you could punch it back into your computer and then convert it from base 64 back into binary. And base 64 uses capital A to lowercase z, lowercase a to lowercase z, 0 to 9, and typically plus and / for the characters that are left. Sometimes you'll see different ones, but most standards use plus and / Base 64 treats each stream of 8-bit bytes 6 bits at a time, which means the output's always a multiple of 4. And if it wouldn't be a multiple of 4, then an equals sign is normally used at the end for padding. It basically just means there's nothing here. So if you see an equals sign, it's a pretty good chance that it's base 64. And you can see an example here where just the phrase base 64 is encoded into base 64. And if you're on a Linux machine, then there's a command base 64, which then you can also give it -d to decode from base 64. And it'll accept stuff from standard input. So you can echo base 64 into base 64, and it should give you that output. Then slightly fancier than just encoding is substitution ciphers. These are the most basic ciphers, where it just replaces one value of input with another value in the output. It's where it gets its name from. And the simplest form of that is monoalphabetic ciphers, where each input corresponds to a single output, and each output also corresponds to just a single possible input. And some basic examples of substitution ciphers are Morse Code, Caesar cipher, and then the more generalized form, shift ciphers. Another form of substitution ciphers is polyalphabetic ciphers, where each input can correspond to several different outputs, or in the opposite, each output could have come from several possible input characters, and a nice example of that is the Vigenere Cipher. And there's a nice website, decode.fr, where there's a whole lot of ciphers that you can just play around with. And some of them it offers encryption and decryption, but also a brute force option if it's feasible to brute force some cipher. Right. So Morse code is a historic example, and most people might not even think of it as a substitution cipher, but it fits the definition. It turns text into a series of long and short tones called dits and das, and they are represented with normally a dot for a da and a dash for a da. No, a dot for a dit and a dash for a da, sorry. And sometimes you'll see words separated by a forward slash, but that's not always. And the encoding it's pretty much based on the frequency of English letters. So that way the more frequent letters have shorter codes, so it's faster to tap them out. And then here you can see just the table of Morse code to your regular alphabet, and you can see E and T have the shortest. It's just a dit for an E and a da for a T. And then you have your less common characters like J and Z and Q have longer four characters in their code because they're not used as often. Then Caesar cipher is another historic and basic example. It just takes each input letter and it shifts it over 3 spaces. So A becomes D, B becomes E, so on and so forth. It wraps around to the beginning, so for example, Z becomes C. And to do it in reverse, you just do it in reverse. A D becomes an A, an E becomes a B, so on and so forth. You get a C becomes a Z. And if you have secret, for example, put it through the Caesar cipher, it becomes BHFQHW. And you can have a generalized form of just a shift cipher, where each letter, they get shifted right or left by a fixed amount, which is used as the key. And each shift of n, so for example, 3, it can be accomplished just as well with an opposite shift of 26 minus 3, so 23. So if you shift right 3, you could also shift left 23 to get the same thing, or left 3, right 23. And for example, if you have the same word secret but shifted 10 times, you get COMBOD as the output. And shift ciphers are extremely vulnerable to frequency analysis because each letter just becomes another letter with no variation in between, basically. So if E is the most frequent letter, if you have a bunch of text with shifted over 10, O will be the most common letter. And then you can make a pretty good guess that each O actually represents an E. And from then you can calculate the shift and then shift everything over to undo it. But that's the more complicated way because the shift cipher, there's only 26 possibilities, so you can just shift it over by 1, shift it over by 2, so on and so forth until you get a sensible result. And a shift of 13 is a pretty interesting is a pretty interesting case because it's halfway through the alphabet. So you shift something 13, and then you shift it 13 again. In either direction, it'll result in the same thing you came with. And the Vigenere cipher, which is a polyalphabetic cipher, it was considered unbreakable for hundreds of years after it was created. And it's basically just a bunch of shift ciphers where you have a key, which is a word, and each letter in the key corresponds to the shift amount for a plain text letter. And the shift amount is based on the location of the key letter in the alphabet. So a key letter of A represents a shift of 0, B represents a shift of 1, so on and so forth. And the key is, you loop through the key as needed if it's not long enough to cover the entire message. So for example, secret, and with a key of word, when you apply the Vigenere cipher, it would become OSTUAH. And since the key isn't long enough to cover the entire word secret, after you've encrypted 4 letters, you would start over with the E from W, and then the T would be shifted with the value of O. And here you can see a nice table where each letter at the top, and then the letters on the side are the key letters. The letters at the top are the plain text letters. So if you have a plain text letter S and a key W, if you start at the top row and find S, and then go down to W, then you would find O. And then you could do the same thing for all of the others. The next thing that needs to be covered before we can go on to fancier forms of crypto is just basic modular arithmetic. Modular arithmetic is just a number system where the integers wrap around at a specific point, so to speak. That point is called the modulus. Another way to think of it is you just keep the remainder when you do integer division. And that's where the remainder division operator, the modulo operator, in programming languages gets its name from. It's normally depicted by a percent sign. Common use case for modular arithmetic that you probably don't even notice is just a clock, especially 12-hour versus 24-hour time. So 1 o'clock is the same as 13 because 1 is congruent to 1 mod 12 and 13 is congruent to 1 mod 12. Or there's 13 is 1 away from 12, and 1 is 1 away from 0, and 12 is 0 away from 12, so 12 is 0 mod 12. And most rules of modular arithmetic, most of the rules of normal arithmetic hold for modular arithmetic. So if you have a number A, which is congruent to a number B mod n, then A plus K is congruent to B plus K mod n, and K times A is congruent to K times B mod n. In each of those cases, K can just be an arbitrary integer. And if you want some more information on modular arithmetic, you can just read the Wikipedia page. It's a fairly decent overview, but it has a lot of math, so you may have to read it over a few times. And XOR is a nice operation because it's equivalent to addition modulo 2, because you can think of it as bitwise addition, but you just discard the carry bit. So here's the table. It's your normal truth table for an XOR, where 0 XOR 0 is 1, 0 XOR 1 is 1. 0 XOR 0 is 0. I think I said 1. But then next to it, I also wrote just the addition. 0 plus 0 is 0. 0 plus 1 is 1. And then on the last row, 1 plus 1 is 1, 0. But we discard the carry bit of 1, so it's just 0. One-time pad is an interesting encryption scheme because it's the only classical encryption scheme that provides perfect secrecy. It relies purely on simple modular arithmetic, where to encrypt something, you just add the key to the message, and to decrypt it, you just add the key to the ciphertext. And one-time pad can't be cracked if you have a few cases. The key has to be truly random. The key length has to be the same as the message length. The key can never be even partially reused, and the key has to be kept secret. If those 4 conditions are met, then one-time pad can't be cracked. But it's not exactly convenient because it requires double the space of the plaintext, because the key is the same length as the message. So if you have 500 words to encrypt, you need 500 letters in the key, or 500 words worth of key, however many letters that would be. It also requires securely exchanging the keys and storing them, because if the key is compromised, then, well, the encryption is useless. And then here's an example where if you have a plain text word, for example, pizzas, and then you have a key as below. So then just, if you want to encrypt that, then one way to do it is just convert the word pizzas into ASCII, and then XOR the key onto there, and then you get a ciphertext as below. Then you have an attacker. Attacker finds your ciphertext, and they're like, all right, let's try to brute force this. They'll come across a key such as 112233445566, that when they XOR the ciphertext with that, they'll get the word secret, and they'll be all excited because they'll think they've cracked it, but it's completely wrong. The actual text was pizzas. And because XOR is an easy way to implement one-time pad, because it's modular arithmetic, then one-time pad is also sometimes just called an XOR cipher or XOR encryption. So these have all been examples of symmetric ciphers, where a symmetric cipher means that the encryption key and the decryption key are the same. RSA is a popular asymmetric encryption scheme, where that means you have a public key and a private key. And one of the keys is used for encryption and the other is for decryption. RSA has found a lot of uses in stuff like PGP keys, SSH keys, as well as TLS, which powers HTTPS. And the security of RSA is based on the assumption that factoring large numbers, specifically large numbers which are the product of 2 primes, factoring those into the 2 primes that were multiplied is hard. And by hard, it means it'll take a long time to compute because we don't know of an algorithm to do it faster than basically brute force. And one thing to note about RSA is that trivial implementations are insecure. And the Wikipedia page on RSA it's a pretty good place to read about the actual algorithm. Now, RSA keys are not terribly difficult to create. You start by choosing two unique primes, P and Q, which you have to keep them private. Then you compute a public modulus, N, which is P times Q. And then you compute the totient function on the public modulus, which then you keep private. And the totient function can be computed as the least common multiple of P minus 1 and Q minus 1. The totient function itself is beyond the scope of this presentation, but the important thing is that it's easy to compute if you have the primes, but given the modulus it's thought to be difficult to compute if you don't have the two primes. And then after that, you have to choose the public encryption exponent, which is a value E, which is greater than 1, but it's less than the totient of N. And E and the totient of N have to be coprime, which means that the only factor that they share between them is 1. For example, 5 and 12 are coprime, but 12 is not a prime, but the only factor that they share between them is 1. And then the last step is you have to compute the decryption exponent, which you keep private. And the decryption exponent is just the modular inverse of E. So whatever number multiplied by E is congruent to 1 mod the totient of N. That value D is the decryption exponent. To encrypt with RSA, and you have a plaintext message M, and you have the public key E and the modulus N, you can compute the ciphertext pretty easily. Just take the message M and raise it to the power of E mod the modulus N, and that's your ciphertext. To decrypt, you have the ciphertext message C, but you also have the private key, which contains the decryption exponent and the modulus. If you want to compute the plaintext message, you just take the ciphertext and you raise it to the decryption power. And one thing to note is that you can't normally raise numbers like this and then just multiply them together when you're doing modular arithmetic like you can in normal arithmetic. But on Wikipedia, if you want to read it, there's a proof on why it works in this case, and then C raised to the D, you're left with M, the original plaintext message. Then here is just an example of creating an RSA key. If you have the primes 61 and 53, you'll compute the modulus by multiplying them together to get 32, 33. Then you'll compute the totient function by just taking the least common multiple of 1 less than the primes, and that becomes 780. And you can choose a decryption exponent, for example, 17, which is less than 780, but it's also coprime. Then you can finally you'll compute the decryption exponent, and After you compute it out, that becomes 413 times 17 is 1 mod 780. And if you want to encrypt, then you just take 65, raise it to the 17th power, and you're left with 2,790 when you're doing it mod 3233. And to decrypt, you have your ciphertext message, which is 2790. And when you raise that to 413, you get 65 mod 3233. And that is the message that you started with. An interesting thing that RSA suffers from is if you encrypt a small message M with a small exponent E, and you have a large modulus N, then C, when you raise M to the Eth power, if it's less than N, then it doesn't matter that it's encrypted because it never wrapped around the modulus, so you can just take the Eth root of the ciphertext and you're left with C. Or you're left with M. Another interesting thing is the Chinese remainder theorem, where if you have a set of integers, n1 through nk, which are greater than 1 and they are pairwise coprime, so n1 is coprime to n2, n1 is coprime to n3, and every other possible combination. And then you have a set of integers a1 to ak, which are greater than or equal to 0. Then there's one and only one x, where x is congruent to a1 mod n1, x is congruent to a2 mod n2, so on and so forth, all the way to x is congruent to ak mod nk. And one way to solve it, which is, this is an inefficient method, but it's fairly easy to do by hand, is you first want to sort the statements by decreasing moduli, and you'll first find a solution to the first two, so that you try each x1 that's congruent to a1 mod n1 until you get an x1 that is also congruent to a2 mod n2. After that, you'll find a solution to the next one, but the difference is this time you're trying each x2 which is congruent to x1, but you have to do it mod n1 times n2 until you get x2 which is also congruent to a3 mod n3. And you'll repeat these steps until you've gone through all of them, but the next one would be x3 is congruent to x2 mod n1 times n2 times n3. And an example of that is you want to find an x which is congruent to 4 mod 5, 3 mod 4, and 0 mod 3. You'll first you'll want to start with all the numbers which are congruent to 4 mod 5. So you'll start with 4, and you have to find a number which is congruent to 3 mod 4. So 4 is congruent to 0. Then the next one is 4 plus 5, since that's also congruent to 4 mod 5. That's 9. 9 is congruent to 1. The next one, 9 plus 5 is 14, is congruent to 2 mod 4. And then the next one, 19, is congruent to 3 mod 4. So now you have to find a number which is congruent to 0 mod 3. So you'll start with 19, which is congruent to 1 mod 3. And then you'll add 20 this time because you already did 5 and 4. So 5 times 4 is 20. So you'll get 39, which is congruent to 0 mod 3. And to test to make sure that it's correct, 39 is 7 times 5 plus 4. It's 9 times 4 plus 3. And it's 13 times 3 plus 0, where you can see the 4, 3, and the 0 are the numbers that you wanted x to be congruent to in the different moduli. This can be applied in certain cases to break RSA encryption, because if you have the same message which is encrypted multiple times, specifically it's encrypted e times, which is the public exponent, and you'll want each p and q are different, which means that each modulus is different as well, and you'll end up with something like this, where you have m to the e is congruent to c1 mod n1, m to the e is also congruent to c2 mod n2, all the way to the last one, which could be more than e, so you have c to the n is congruent, m to the e is congruent to cn mod nn. And since you already know e, all you're really for testing finding here is m, even though you're finding an m to the e that is congruent to all the different ones. Once you find an me that's congruent to c1, c2, all the way to cn, you'll have the plaintext message, which was originally encrypted. All right. And that's the end of that presentation. Is there any questions here? Let's see. No questions? Let's see, was there any on? Someone on YouTube says one question, I think. Oh, for RSA. Well, there's two totient functions. One is the Euler totient function, and then one is the Carmichael totient function. The Carmichael totient function is the one that I explained here, where you take the least common multiple of p minus 1, q minus 1. The Euler totient function you can compute for n is p minus 1 multiplied by q minus 1. Now, the Carmichael totient function results in slightly smaller values than the Euler totient functions. Well, sometimes it does, because p minus 1 times q minus 1 can be larger than just the least common multiple of p minus 1 and q minus 1. Does that explain it? All right, cool. All right. For the one-time pad slide, would you see that, the key that has 0x at the beginning mean it's hex? Let me see. Yes. The 0x, that's just to denote that it's a hexadecimal, or in this case, it's really a binary value, but it's the hexadecimal representation. And below, you'll also see 5049 5A 5A 41 53 is the hexadecimal values of the ASCII values for P, I, Z, Z, A, and S. Cool. Is there any other questions? For CTFs, how can you figure out if you must use Euler or Carmichael? They should result in the same result. The reason that you can use one or the other is it's beyond the scope of the presentation, but there is a fancy number theoretic reason that you can use one or the other. But you can read it on Wikipedia on the RSA page. It explains it a little bit, but you have to click through a few links if you want the full reason. All right. Chinese remainder theorem? All right, let's see. Which part? Which part of the Chinese remainder theorem? How it works. All right. So how it works is the number you're trying to solve for is the x, and you have numbers a1 through ak, and then you have n1 through nk, which are the moduli. And basically it says that there is only one x which is congruent to a1 mod n1, a2 mod n2, so on and so forth. But it could also mean that there's only one x that, hold on, let me check my notes here for that. Exactly what I'm trying to say. All right, so you could also put it that there's only one x that when you divide it by n1, you get a1 as the remainder. When you divide it by n2, you get a2 as the remainder. And when you divide it by nk, you get ak as the remainder. That's another way to look at it other than just x is congruent to a1, x is congruent to a2, x is congruent to ak. And here in the example, you're trying to find a number x which is congruent to 4 mod 5, which is congruent to 3 mod 4, is congruent to 0 mod 3. Or in other words, you're trying to find an x that when you divide it by 5, you get 4 as the remainder. When you divide it by 4, you get 3 as the remainder. And when you divide it by 3, you get nothing as the remainder. So the first numbers you have to find are all the numbers which are congruent to 4 mod 5, or when you divide it by 5, you get 4 as the remainder. And for each of those numbers, you also want a number that when you divide it by 4, you get 3 as the remainder. So here, you start with 4, you divide it by 4, you get 0 as the remainder, or in other words, it's congruent to 0 mod 4. And then the next one, is 9 because if you divide 9 by 5, you get 4 as the remainder. So then you'll try 9, you'll find it's congruent to 1 mod 4. And you'll keep going, adding 5 to the number each time until then you get to 19, which is congruent to 3 mod 4. So then you need to find x that's also congruent to 0 mod 3. And that means when you divide it by 5 and 4, you get 0 as the remainder there. I think. No, I said that wrong. You already have a number that when you divide by 5, you get 4, and when you divide by 4, you get 3. But you need to find a number that when you divide it by 3, you get 0 as well. So then you have to do 5 times 4, or 20. You have to add 20 each time, and then the next number is 39, which then when you divide it by 3, you get 0. So then you have 39 is 7 times 5 plus 4, which means it's congruent to 4 mod 5. It's 9 times 4 plus 3, which means it's congruent to 3 mod 4. And it's 13 times 3 plus 0, which means it's congruent to 0 mod 3. Do you mean if you divide by 3? I think, did I cover that? Okay, cool. Yeah, it's an interesting thing, the Chinese remainder theorem. It definitely requires kind of playing around with it in your head before it makes any sort of sense. Because like a lot of things in math, it seems like magic. Is there any other questions? Chinese remainder theorem commonly found in CTFs? Yeah, I've seen several challenges where the Chinese remainder theorem is used to crack an RSA key, or I guess a message encrypted with multiple RSA keys, which in that case is the flag. But it's pretty easy to tell that you need to use the Chinese remainder theorem because you'll have multiple different ciphertexts and moduli given in some form. So then from there, I guess the easiest way is to just try to apply the Chinese remainder theorem. And you don't have to do it by hand. You can write a program for it because it is fairly algorithmic. It shouldn't be too difficult, especially if you have something like Python where you can script it fairly easily. I'll get to that in a second. Show an example in Python right now, or would it take too long? I don't think I have an example here right now. It will take a little bit too long to code it up, because it is something that you will probably not get it right on the first try. I know I didn't, and I don't think I have that program laying around anymore. I think I lost it and I accidentally deleted a virtual machine. I haven't used that, but probably. It's probably pretty well written. How do we find the plaintext using the Chinese remainder theorem without knowing the private key? That's the whole thing you're solving for. X, in this example here, you can think of that as the message that's encrypted, and 4 is one of the ciphertexts, 3 is another ciphertext, and 0 is another ciphertext. And when you're solving for X, you're solving for the plaintext message, but then if you look here, it's actually message raised to the eth power, but you already have the exponent because that's part of the public key. So that's not an issue. So in this case, you're just solving for an m raised to the e that's the first ciphertext, but it's also the second ciphertext and all the way to the last ciphertext. Does that make sense? It is raised to the exponent, yes. I believe so. Because that is what you're solving for. You already know the exponent. That is a lot of stuff in that repo. Okay, yeah. No, but it does have a lot of neat stuff. I've used it past. Not so much for crypto, but for scripting remote connections that I need to put a shell code for. I think there was one question here, QWE. Was your question covered? Oh, it wasn't a question. Can you repeat it, I guess? I already forgot what it was. Oh, multiple ciphertexts lying around? As long as they're not the same message. As long as it's not the same plaintext message. No, you probably shouldn't leave them lying around. Well, you can crack them as long as you have exponent number of them. So if you have a really large exponent, you'll need a lot of ciphertexts. So if you have an exponent on the scale of 65,000, then you'll need 65,000 ciphertext. And the odds are that you will not have the same message encrypted 65,000 times. So in that sense, it should be fine, but these also only apply to the trivial RSA where you don't apply any extra security enhancements, I guess, such as padding the message to be as long as the key, which will make for example, the eth-root attack not work, because if you pad the message to be as long as the key, then when you or as long as the modulus, which I guess that's as long as the key, then when you raise it to an exponent, it'll pretty much have to cross over the modulus, and it'll wrap around, meaning you can't just take the eth-root of the ciphertext and get the message anymore. Is there any more questions? Found a tool. Interesting. Yeah, that looks like a nice little script for it. Is there anything else? All right. Decode has a Chinese remainder theorem solver. I wouldn't be surprised. They have a lot on there. All right. Well, yes. Have a great night. Yep. Thanks for coming.